to bear with me. This is the first time that I've done one of these webinars. But anyway, we'll give it a shot here. Welcome to the Electrical Safety webinar. We're going to talk about NFPA 70E 2015, NFPA 70, which is the National Electrical Code, the 2014 edition, and a little bit about OSHA, the Occupational Safety and Health Act. I want to say a few thank yous to get started. First of all, I want to thank EasyPower for giving us this opportunity to get one of you guys and to try and encourage you a little bit to be safe out there. I want to say thanks to Miller Electric here in Omaha, the electrical company here that I do a lot of work with. They do arc flash studies and short circuit studies and so forth. And they have the same passion and desire about being safe as I do, and so it's a good fit. Thanks Scott Love, the safety director, Barry Overman, who is in charge of proposals and labeling, and all the others who are involved in that. And I want to thank all of you who are in attendance. My name is Robert Weber. I will be your instructor. I'm an OSHA compliant instructor. Of course, OSHA does not certify or recommend anything, but I'm able to say that I'm compliant with what they're looking for. I'm instructor of General Safety and Industry, CFR 1910, which is Code of Federal Regulations. That's for your industrial plants and so forth. And then CFR 1926, which is Code of Federal Regulations for construction, building buildings and so forth. This is some of my background. Contractor or master electrician in 5 different states. Electrical Inspector Certification by IAEI, which is the International Association of Electrical Inspectors. I do electrical consulting, PV solar designer, inspector, and consultant, and recently certified by NFPA, the CESC, Certified Electrical Safety Compliance Professional. So I am very concerned with electrical safety and the electrical industry. And again, I thank you for giving me the opportunity to put this presentation on. We're going to be talking about NFPA 70, the NEC 2014 code. I do that instructing. I have code classes. We'll get to that in just a moment. NFPA 70E, standard for electrical safety in the workplace. I do instructing, put on seminars and code classes for those. I've been in the field since 1973. To the different types of jobs that I've worked on, and I'm putting that up there to let you know that I have been around for a while and I do speak from experience, and hopefully today I can share some things that will make you a lot safer out there. My contact information I put up. The phone number is 402-612-2949. I put that up there. You are welcome to give me a call at any time between 8 and 5, Monday through Friday, an electrical code question. Now, I used to say call me at any time with a question, but I've since decided to say Monday through Friday, 8 to 5, with an electrical code question to kind of involve in the questions that I get. My email address is azez123@questoffice.net. Again, you are welcome to email me with code questions or comments about the program or questions on different programs that I have available for training, and I will respond to those. Anybody have any idea what that stands for? The first part. Okay, are you ready? It stands for as easy as 1, 2, 3. Right? So that way it'll be easy to remember, and when you type in the email and so forth, it should be able to come to mind really quick. www.continuingelectrical.education.biz is my website. If you put that in the Windows bar of your computer, not the Google bar, it will bring my website up. You will see a plateau out in the desert, which has nothing to do with electricity. I just like the picture. Anyway, you'll see the available sites that I have there for the different classes, 14 different classes, along with exam prep classes, electrical theory classes, calculation classes, and so forth. I always take a minute to thank you, the audience, for giving me the opportunity to help you gain a better knowledge and appreciation of electrical safety. and to help you improve your electrical and safety skills. Now about the program, standards and codes say what they say. I'm showing you what they're saying by referencing them and giving my opinion from my experience, study, observations, training, and so forth. All of us have opinions, and that's great, but the standards and codes say what they say. And we need to think about this as we read them and use them. Sometimes what we're taught is not exactly what the standards and codes say, and because they change so often every 3 years because of advancing technology and more information, we really need to keep up to date on it. I believe in education. It's more than just continuing education credits. And I want to take this moment also to tell you people out there that you are important people. You are the lifeblood of the world. What do I mean by that? Well, there's about 8 million people in the world, and we in the electrical industry or the electrical trade are very minimal. And we keep them in comparison to that, and we keep the lights burning. So feel good about what you do, and feel good about being safe out there. We've come a long ways in our understanding of electricity, haven't we? We look at a slide like this and we think, you know, smile a little bit, and then we begin to realize what's happening. And all of a sudden we become rather horrified. What in the world is that gentleman doing with his young child throwing a switch to an electrical disconnect? I realized that they didn't have proper PPE back then. It also illustrates the understanding of electricity, dangers involved, and so forth. We've come a long ways, wouldn't you say? How many of you in the audience out there would allow something like that with your employees, let alone your children? And yet, like I said, we've come a long ways. And so we need to have an open mind. We're learning a lot of things. We're going to learn a lot of things here today. But hopefully this will illustrate the need for education. Electricity is a wonderful energy, but we need to know what it is we're doing with it. The principle of safety is what I try to teach. I don't try to approach this from the standpoint that it's the law, federal law, OSHA is, because it is. I don't try to approach it from the standpoint of they'll fine you or you could get hurt because you will. The principle of safety is where I try to come from. Laws are based on principles, and laws can change. Isn't that true? But principles do not. Principles do not change, and safety is critical. We can get anything to work, can't we? Now again, we smile at something like this until some water comes down that gutter and winds up getting into the electrical meter socket and shorts it out, and then we have huge issues real quick, don't we? Okay? So we can get anything to work. Standards, NFPA 70 is the NEC 2014. NFPA 70E is the standard for electrical safety in the workplace. Yes, NFPA produces both of these publications that we use in the electrical industry. And then there's OSHA. We're going to get into how all of these things relate to each other and how we can use them to our benefit. NFPA 70, the NEC, first of all, that stands for the National Electrical Code. If you electrical contractors, journeymen, electrical engineers, and things in the audience out there understand that NEC stands for the National Electrical Code, but NFPA, it's an NFPA document. Okay? What is it? Well, Article 90 says that it is for the practical safeguarding of persons and property from the hazards that arise from the use of electricity. Wow, I thought electricity was safe. Well, for the most part it is, but there are hazards involved. Have you ever plugged into a wall socket and had it short out? Have you ever turned a light switch on and had a light bulb explode or a fixture explode or turned a disconnect on and something happened? There are hazards involved with electricity, and because it is so commonplace, so much a part of our life, we tend not to think about it, and we should. What it is not is it is not a design manual. It's not an instruction manual for untrained persons. That's in Article 90 of the code also. Why do we need it? Well, because of the nature of the energy, and we're going to learn a little bit about that as we go along here, we must be very careful with the installations that we install. Every nut, every bolt, every screw that we touch as electrical engineers and electricians has a code rule. Why? Because it's important. The color green, for example, for ground, that is a safety. So we know the difference between the grounded, the ungrounded, and the equipment grounding conductors, the color white, and so forth. And so we need to be able to know how to install our wiring methods, what wiring methods to choose, and so forth. NFPA 70E, okay, that is an NFPA document also. It's standards for electrical safety in the workplace. What is it? Well, I'm going to read to you right out of 70E as what it is or what it was meant to do here. So bear with me just a moment. It says it much better than I can. It says the purpose of this standard is to provide a practical, safe working area for employees relative to the hazards arising from the use of electricity. It says the standard addresses electrical safety related work practices as opposed to installations, safety-related maintenance requirements, and other administrative controls for employee workplaces that are necessary for the practical safeguarding of employees relative to the hazards associated with electrical energy during activities such as the installation, the inspection, the operation, the maintenance, and the demolition of electric conductors, electric equipment, signaling and communications conductors and equipment in raceways. This standard also includes safe work practices for employees performing other work activities that can expose them to electrical hazards, as well as safe work practices for the following. It talks about the installation of conductors and equipment, installations used by electric utilities, and so forth. If you don't have a copy of NFPA 70E 2015, I strongly encourage you to get one. And the most important articles, I think, are Article 90, Article 100, which is definitions, and so forth. And we're going to learn as we go along here that definitions are critical, understanding the language that we use. All right, so why do we need it? Well, NFPA 70, the NEC, tells us how to install things correctly, but it doesn't tell us how to maintain them. It doesn't tell us how to work on them safely if we're around them. OSHA comes into play, the Occupational Safety and Health Standard. What is it? It's federal law. 1970, the Occupational Safety and Health Act was put into play. I'll give you a little brief synopsis of why that was. It's my understanding at that particular time that the Vietnam War was going on, and about 14,000 servicemen were killed in that war in 1970, and another 54,000 were wounded. Well, that was in a war. Now, in the very same year in this country, over 2.2 million people were injured or hurt or died in work-related incidents. That's at home, not across the sea in the country. Something's wrong with this picture, wouldn't you agree? Okay, so the Occupational Safety and Health Act, why do we need it? Well, it's got what's called the General Duty Clause that states that we have the right to have a safe workplace, okay? That hazards in those workplaces be identified. But the interesting thing about this, and we'll as we go along, the OSHA standard tells you what to do, but it doesn't tell you how to do it. Okay? So we'll see that as we go along here. They work together because NFPA 70, which is the NEC, the National Electrical Code, talks about safe installations. What size conduit do you use? What size wire do you select? What's the insulation rating for conductors? What's the environment that you're putting it in, and so forth. Just a number of different things and variables to take into consideration. The electrical trade is a skilled profession. We're not a bunch of guys drilling holes and pulling wire. It is a skilled profession. Okay, we need to know what we're doing when we install these systems. Our electrical inspectors are there to help us. They're up on these codes and they're paying attention, and they help us when we make a mistake. That saves us, that helps them, and that helps the general public. 70E, Safe Work Practices, on the other hand, doesn't focus so much on the actual installation, but how do you deal with hazards? How do you identify them? How do you recognize them? What are you looking for? Something interesting to think about is if you install an electrical panel, say rough it in building, it's not energized yet, the cover's off, you got the circuits tied in, and you look at that. Now, keep that thought in mind, now when the drywall is on and the panel is energized and that cover's off, look at it again. You don't see any difference. How do you know if it's energized or not? It looks the same. Okay? So 70E tells us, hey, here's what you need to do. Here's what you need to be aware of. Here's how you need to test this. Here's what you need to look for, and so forth. And so that's how these standards work together and help us. And then, of course, the OSHA standards gives us the right to be safe when we do our work. It's a little different for me talking and not seeing people in front of me, so I'm going to not ask for a show of hands, but I'm going to ask you to think about this for a moment. How many of you have families? Okay, most of you out there have families. You have a wife and children, or you have people that are close to you. How many of you or your families could get along without you, or if you were laid up or injured in an electrical accident that could have been prevented had you understood what was going on, the safe work practices, and been able to follow them? Pretty sobering thought, isn't it? So what we're trying to do is see how all three of these are tools that we can use to keep us safe, so we can continue to and help our employer out. He can keep us safe. He can continue to produce widgets, and we can continue to help in that regard, and everybody can provide for families and be safe in doing it. That's kind of in a nutshell how everything works together. The standards are there to protect life, to protect property, for health and well-being. However, the one thing that you must remember is that the standards are a minimum. They are not maximums. We can always do better than the minimum, don't you think? It's based on the premises of what is an acceptable outcome. Now, what does that mean? Well, some of these standards and codes, they're so minimal that an acceptable outcome, for example, would be if you limit the exposure to a burn from 2 calories or second-degree burn to a 1.2 calorie per centimeter burn. Is that an acceptable outcome? Well, I don't think any burn's an acceptable outcome, but apparently it is because the standard accepts it. So that's an example of what I'm talking about. And that's why it's important to get education and to understand how all these things work together, why we need arc flash calculations, the incident energy, why we need to install things properly, and so forth. So the standards, you could say, were written in blood and destruction. That's a pretty sobering thought. Each standard and rule in these standards, if you look at the history of why that rule is in there, is because somebody lost their life, or there was damage to equipment, or destruction to property. And I mean, realistically thinking, that's why those rules are there. They're not a government bureaucracy type of thing to hurt us, although I'm the first to admit that anything can happen. But the basic idea behind these standards is they're a tool. They're there to help us be safe and to enjoy the electrical energy that we use. The minimums in Article 90 in the NEC and the NFPA 70E state what those minimums are, that they're for practical safeguarding. Here's how I illustrate that. Safety in cars, for example. If you were driving down the road, an Army tank would probably be a lot safer than a car. Wouldn't you agree? That's not very practical. Now, seat belts in cars are a minimum safety standard, and that's practical. Okay? So that's the precept or the concept behind it. And safety is going to cost. It's going to cost one way or another. It's going to cost to get education. It's going to cost to set up training programs and educate your people. But I'm telling you, those costs are going to pale into insignificance if the other costs come into play with lawsuits, destruction of property, and forbid it, the loss of a life, or maybe not being able to work, not being able to provide for your family and so forth. So if you think about it, if you think education is expensive, think about ignorance or the lack of concern or lack of education. Right? Electrical safety. Hopefully none of you have been in the situation that this gentleman's in here. Electricity is essential to modern life. If you think about it for just a moment, what if electricity quit tomorrow? And I mean every bit of electricity, batteries, electricity, everything. The world would be a tremendously different place. It would come to a grinding halt, would it not? So, like I said before, there's a few of us in comparison with the many people in the world that are keeping the lights burning, that are keeping things going. Some employees work with electricity directly. Those of us who are electricians and inspectors and apprentices, journeymen, and so forth, and some indirectly. Maybe you're operating a machine that's got electrical to it, but maybe it's got water pressure to it. Maybe it's got hydraulics to it also. Some of us are plugging in computers and plugging in battery chargers and those types of things. So electricity is a serious workplace hazard. Electricity can be productive and safe, but why is safety so important? Let's talk about electric current for just a moment. All of this is going to help you to appreciate these standards a little bit more. Did you realize that electrons travel at approximately 186,000 miles per second? That's pretty fast. It can be lethal in milliamps. That is thousandths of an amp. Examples, GFCIs, that's ground fault circuit interrupters for personnel. The trip levels for GFCI receptacles and breakers are between 4 to 6 thousandths of an amp. Why? Well, let's take a look at it. You have a 120 volt circuit. The human body has a resistance of approximately 1,000 ohms. So to see the relationship, we have the voltage, which is E, divided by the resistance, which is R, which would then give us the current flow. At the bottom of the screen, we see 120 volts divided by 1,000 ohms is 0.120 amps or 120 milliamps. And you might say, okay, so what? Well, look at what the damage level is. 4 to 6, you're at 120. That's 20 times the amount of current that the human body can withstand. 20 times. Now, if you do the same thing with 240 volt, 277 volt, 480 volt, etc., you begin to get the idea as to what we're talking about. Now, I got a clip here that I'd like to show to you. I'm going to see if I can get it to work. All right, I'm going to take just a minute here. I apologize for the quality of this. It's the computer is a little older computer and so forth. But you see the 1, 2, and 3, that stands for 1 foot, 2 foot, 3 foot. This is a gentleman. I'm sorry, not a gentleman. You've heard of car crash dummies? Well, these are arc flash dummies. In other words, they're mannequins that they use to test. And this is what the basis of the codes and rules and regulations and calculations that we use in NFPA 70E. These are disconnects, and this would be like a person working in front of this. All right? What would happen? Well, you saw an arc flash. Well, let's look at the label over here to the left. See where it says equipment? That's a 200 amp disconnect. If you go down to test parameters, you see that the voltage is 480 volt. The available short circuit current is 11.4 kA. What does that mean? That's 11,400 amps. The cycles are 12 cycles. Well, what is that all about? Well, we have in this country a 60 hertz system, which means 60 cycles in 1 second, 60 seconds in a minute, and so forth. So in 12 cycles, less than a second, at a distance of 12 inches, this is the kind of damage that can happen on a 200 amp disconnect at 480 volt. Now you'll notice calculated incident energy per IEEE 1584. Those are the calculations in NFPA 70E. We're not going to get into those today. But this is all critical. It's all important, because if somebody were in front of that, you could wind up doing some serious damage in a heartbeat. Okay? Now I'm not sure this next one is going to work, but again, it's food for thought. Typical day at work. Now we're going to stop and look at that for just a minute. That was obviously a reenactment, because if it were real, those two gentlemen would not have rolled apart like that. But look at all of the things. I would like to say what's wrong, but I would like to ask Sipler what was right with that whole situation. First of all, they were working equipment live. Second, they had no personal protective equipment. They're on a concrete floor. The house cleaning was terrible. No instruction on what to happen if somebody gets into can't let go. That's the last thing you do, is run up and grab, somebody who's into can't let go, because now you're into can't let go. 70E and understanding how that works helps to protect against all of this. And the sad part of it is every piece of this video clip could have been prevented. Pretty much every piece of it. And those electricians would have been just fine, and there would not have been another incident. So this is just a sample of what I teach you to do in the classes, how to use 70E. And really, stop and think about it, gentlemen and ladies. Is it really hard to put on the right pair of voltage-rated gloves? Is it hard to put on a pair of arc-rated glasses? Is it difficult to wear clothing that's arc-rated? Is it expensive? Well, you might spend a couple $100s in PPE, but let me ask you this. When was the last time you went to an emergency room? Okay, what did that cost? What would that cost? What would it cost if you had to be at a burn center, and so forth? So what I'm trying to help people to appreciate and understand is sometimes we have to change our paradigm of things and look at things from a little different angle, and then it begins to make a lot more sense. Okay? The vocabulary that we use in these documents, whether it's the OSHA document, the NFPA 70, the National Electrical Code, or NFPA 70E, we've got to understand the vocabulary, the language that's being used, and the definitions. That's why I encourage people, please read, I don't know what that's all about, hope you can't see that, to please read the definitions and understand the terms, because you're not going to understand what the code means if you don't understand the terms that are being used. Don't use industry slang. We have a lot of slang out there, and some of us know what we're talking about, and some of us don't have a clue, because we have different slang for different parts and pieces that have a general term for it. All right, there are misconceptions and myths about electricity. We're going to look at some of those. There's electrical shock and other injuries that are involved, electrical hazards, electrical safety for maintenance. We work really hard at putting systems, installing them safely. How do we maintain them? And along those lines, how many of us maintain our electrical systems? You're probably out there going, what do you mean maintain my electrical system? What are you talking about? Well, let me give you a couple of for instances. Do you ever suit up and put on the proper PPE and take the panel covers off and make sure there's no dust and dirt accumulating inside of your equipment? Do you turn your circuit breakers on and off once a year according to manufacturer's recommendations? Because there's a lubricating grease on the trip mechanism that allows that to trip in 0.008 of a second like it's supposed to. Would you agree with me that dust and dirt and corrosion and heat under load or no load and so forth would start to break those circuit breakers down, the very usage of it? Of course it would. How many of you test your GFCI receptacles to make sure that those buttons work? Probably, I have heard at one point that 12 out of 100 fail in the on position. They have what's called MOVs, metal oxide varistors. Well, those are an electronic part. How can that be something that's subject to damage? Well, think about it. What does a lightning event do to our electrical systems? Now, I'm not talking about a lightning strike. If lightning strikes something, it's toast. It's over, right? But doesn't a lightning event generate voltage and current on all metal parts? Sure it does. And those large voltages and so forth can take out those electronics and wind up failing in the on position. That's why there's a little maintenance schedule in each box that you're with your breaker and with your GFCI receptacle that you test it January, February, March, and so forth. Yeah, I know that's the stuff that we throw away. That all that is just a bunch of extra garbage, right? Well, no, testing that needs to happen. What about testing your emergency lights and so forth? If batteries sit and they charge and charge and charge and you don't exercise them, what could happen to them? Well, again, rust and corrosion and that sort of, everything that we put together, once it leaves the factory assembly line and heads out, starts to go back to its natural state, doesn't it? It starts to break down, and through years and years of use, it begins to go back to where it came from, the elements it was made from, much like the human body going back to dust, right? All right. So electrical safety for offices and classrooms is important. Electrical education. Vocabulary. What is voltage? What is low voltage? What is high voltage? What is current? Resistance? What's a conductor? An insulator? What is Ohm's law? Let's take a look at some of these. Voltage is electromotive force, and it is a property. It's electrical potential, energy, or you might liken it to pressure. It's the pressure that pushes the electrons along. Voltage is a property that's measured in volts. Low voltage, of course, is a relative term. Electrical installations and electrical equipment operating or intended to operate on systems of 600 volts nominal or less is usually considered by low voltage. However, those of us on that side of it, in the 480 volt side, would consider that high voltage. Okay? On the utility side, they would say it was low voltage because it's under 1,000 volts. All work that's performed directly on or in proximity to, now those are important words to think about, to such electrical installations, equipment, or systems, that's what's covered under the term low voltage. Same with high voltage. Electrical installations and equipment operating are intended to operate on systems of more than 600 volts. Any work or all work that's performed directly on or in proximity to these electrical installations, equipment, or systems fall under the high voltage range. That's beyond the scope of this training, but it helps you to appreciate that terms are important. Okay? Current. It's the continuous movement of electrons past a given point. Again, current is a property. It is measured in amps. Sometimes the symbol I is used instead of A. Why I? Because when they were first discovering current flow, they called it intensity. Okay, so some of these symbols and so forth will make sense, again, if we understand what they stand for. Now, resistance is the opposition to the movement of electrons. The resistance is used for direct current. It's a property. It's measured in ohms. Impedance is the proper term for alternating current. And then we have reactance, capacitive reactance, inductive reactance, and those are invisible resistances. It's an effect. Now, resistance is commonly used to cover all of these, but it's a property and it's measured in ohms. Okay? Properties. What are properties? I've been talking, well, let's go back one. Distance is a property. It's measured in inches, feet, and miles. So voltage is a property measured in volts. Current is a property measured in amps. And resistance is a property measured in ohms and so forth. Okay? What is a conductor? Is it a person who collects tickets on trains or a person who leads an orchestra, a band, or a choir? Now, when we're talking about a conductor, it's a substance or a thing that allows electricity or heat to flow by passing energy from particle to particle. Conductors such as silver, copper, gold, aluminum. We also have conductive metals like our EMTs and our building steel. We have conductive dusts such as coal dust and that sort of thing. Metal dust, we have conductive gases. Yeah, conductive gases we get into with these incident energy calculations. We don't have any calculations for them. We'll get into that coming up, but this is all a part of it. The human body is conductive, as we looked at before. And the reason they say a conductor, not a wire, is because a wire is a type of conductor. A metal pipe is a type of conductor, and so forth. And that's why when you say conductor, it's any substance or anything that allows electricity or heat to flow by passing energy from particle to particle. So see how our understanding of these different terms that we use on an everyday basis hopefully is beginning to make a little difference in our thinking patterns? What is an insulator? Well, it's a barrier that wraps conductive materials to protect against electric shock, or a material with little or no conductive properties. It's got super high resistance. Okay? Glass, rubber, mica, and some plastics and so forth would fall into this category. Okay? Ohm's law. This is the law that every electrical engineer, every electrician, every journeyman, every apprentice, anybody that's working in the electrical field should know this law inside and out. It is not difficult to understand. It is not difficult to use. The beauty of it is its simplicity and the fact that the formula never changes. The numbers do, but the formula never does. Let's take a look at it. R stands for resistance. That is the relationship of the voltage divided by the amperage. We looked at that earlier. 1 volt will cause a current of 1 amp to flow through a conductor having the resistance of 1 ohm. Okay? Pretty simple, straightforward. You are no doubt familiar with this very, 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 very simplified Ohm's law wheel. And again, the beauty of this is if you know what the voltage is and you know what the amperage is, you can find out what the resistance is simply by covering the letter that you're trying to find. So if you put your thumb over R, you're trying to find resistance and you have the voltage and the amperage, the formula is volts divided by amps. Now move your thumb to the left and cover the amps. If you want to know what the amperage of a circuit is and you have the voltage and the resistance, there's your formula, voltage divided by resistance. If you want to know what the voltage is and you have the amperage and the resistance, cover the V, and there's your formula. Amps times resistance will give you voltage. Very simple, right? It's unbelievable how many people forget that, myself included, when we start working with electricity. We have a circuit here, and this is a very simple circuit. We're going to go through this just a little bit to see how this works. And all of this is designed to help us appreciate why we have 70E, why we have 70, the NEC, and why OSHA says, be careful, you must wear what's appropriate. You must be safe. We have a general circuit here. What is the voltage of the circuit? It's 120 volts. Do you see that? We have a 20 amp overcurrent device. We're going to say that this is 12 gauge wire. We have a 120 volt load. Now if you follow the circuit, it comes from the source, which is the transformer on the left, goes to the overcurrent device. At this point, we'll just say it's going to travel through the load, and then it's going to return on the neutral back to where? Ground? No, to the source. And then it goes all over again. So the Greek word for circuit is circle. You have to have a complete circle or a complete circuit for current to flow from the source through the load back to the source. But what happens if you wind up with a fault? What if the current starts going somewhere that it's supposed to go? Well, look at the amperage on that meter. How many amps is that showing? 600 amps on a 120 volt circuit. How in the world do we get 600 amps on a 120 volt circuit? Well, we're going to walk through that here for just a moment. Show you how Ohm's law works and why we have 70E. The voltage is 120 volt. The circuit distance we're going to say is 50 feet. Now if you have a circuit that's 50 feet away and there's 2 wires, what's the total footage? 50 foot? No, it's 100 feet. It's got to go down 50 and back 50, correct? So it's 100 feet. We're going to say the load is 7.5 ohms. What is the amperage, or what is the amps that that's drawing? Well, 120 volts divided by 7.5 ohms will give you 16 amps, correct. Now, as we examine this circuit, we find it dead short, and we got to find out, well, what's happening here? How do we get 600 amps? Well, the conductor is a 12-gauge wire because it's a 20-amp breaker, and we know the AWG stands for American Wire Gauge because in the NFPA 70, National Electrical Code, in 110.6, it tells us conductors are going to be copper unless otherwise specified. I'm sorry, that the gauge is American Wire Gauge. The conductor is going to be copper unless otherwise specified because in 110.5 of that same standard, it tells us it's copper unless otherwise specified. If the circuit is 120 volts, the amps on the meter is 600 amps, that is going to be the fault current. And here's how we arrive at that. If you go to the resistance of the circuit, the wire, number 12-gauge wire, in the National Electrical Code, Table 8, 12-gauge wire has a resistance per 1,000 feet of 1.93 for resistance, for solid. We have 100 feet of wire, correct? Now, because the table is in 1,000 feet, I'm going to show you a little trick here. If you want to know what 100 feet is, put the decimal point here, 0.100. For 10 feet, it's 0.010. For 1 feet, it's 0.001. Okay? Here's why we're doing this. The total resistance then would be 1.93 per 1,000 feet times 100 feet to get our total resistance. So 1.93 times 0.1 gives you 0.193 ohms resistance. Now we have our voltage and we have our resistance. How many amps of current flows on that 50-foot run? Ohm's law, voltage divided by resistance equals current. 120 volts divided by 0.193 ohms of resistance gives you 621 amps. Now you think about that for just a minute. That's a 120 volt circuit. The distance is 50 feet. That's on an infinite bus calculation, but the principle is the same. That's how we get high fault currents. That's why our breakers are designed to interrupt them. That's why we need to know and we need to understand. What are we doing out there? What are we working with? How many of you realize that on a 120 volt circuit there was that amount of current available? Do you think that this could do some damage? It's approximately 1 degree of heat per amp. So at 621 amps, at 621 degrees of heat, blasting at us under 120 volts of pressure. This is not on a big motor circuit control panel. It's on a circuit in your home. NFPA 70, the National Electrical Code, will tell you how to install that circuit correctly. The size of wire, the size of overcurrent device to erupt when something like that might happen. 70E will tell you how to work on that circuit safely if it's in a commercial location. Do we have 120 volt circuits in commercial locations? Absolutely. Okay? And then, of course, the OSHA standard is for other than dwellings, but it tells us to be safe. Okay? So does any of this make sense? It should. The very fact that you've tuned into this webinar indicates that you have an interest or a need to understand this, and you are to be commended for that. And I'm very privileged to be able to bring some of this information to you. Education is absolutely critical. Codes and standards are critical. PPE, which stands for Personal Protective Equipment, and the proper use of it is critical. The National Electrical Code, NFPA 70, its proper use is critical. 70E and its proper use is critical. OSHA in other than dwelling units, understanding that is critical. These are tools of the trade, guys. How many of us know how to use these three implements, these three tools? Hopefully we're learning how important it is to understand what it is that we're dealing with. Now, you might see a lot of this, these codes and standards, and go, oh my God, it's the elephant in the room. We're overwhelmed. Well, take heart. I'm going to use an analogy here that hopefully will help you. Here's the question. How do you eat an elephant? One bite at a time, okay? How do you make your place of work safe? One step at a time. But you got to make the step, okay? You got to start. We got to start with education. then we got to start with everybody understanding and everybody being on board. We design and install electrical systems to work, don't we? But what happens when they fail? Okay? Do we design them so that they fail safely, so they won't kill people? Do we train our people to be aware of what's possible? It's not if systems fail, it's when they fail, because they will fail at some point. The National Electrical Code, NFPA 70, in 110.9 talks about interrupt rating. 110.10 talks about withstand rating of equipment and breakers. Do we know what that is? It's stamped on every breaker. It's in the product safety or the product standards. It's on every label on the inside of a disconnect or a panel. We never look at it. Isn't it true that the instructions are the first things we throw away, especially as guys? How many of you guys out there, when you're putting something together for your kids, do design build? I know I do. And then when it doesn't work, you got to go get the instructions to figure out how it works. 110.16 talks about arc flash warning. 110.24 talks about short circuit current availability. Why? Why are all of these things coming into the code? Why is there so much attention to this? Because it is a dangerous energy. It's a useful energy, but it is very dangerous, and you can get into trouble very, very quickly. NFPA 70E tells us how to recognize hazards and how to deal with them safely. Now think about it for a moment. 70E is the standard for electrical safety in the workplace. It doesn't say standards for plumbing safety. It doesn't say standards for HVAC or carpentry. It's standards for electrical safety. Okay? This is our industry. It's our trade they're talking about. Okay? It's been around since 1979, and we are just now getting on board. Okay? How do you recognize, first of all, how do you deal with electrical hazards safely? OSHA will tell you to deal with it, but 70E will tell you how to deal with it. Let's go through a couple of misconceptions here. We're starting to run out of time, so I'm going a little quickly here. Electricity tends to go to ground. After it reaches ground, it disappears. Misconception 1. That's incorrect. Ground serves as just one of the electrical loops that misdirected current can use to get back to the grounded power source. The earth is a great conductor. Connections to it isn't very good, and that's why it's not an effective ground fault current. Next, misconception number 2. If an electrical appliance or tool falls into a sink or a tub of water, the item will short and trip the circuit breaker. Not necessarily so. Why? Because the sink or tub may be non-conductive. Plastic. Do we have plastic sinks and tubs? Yeah. Therefore, not a part of the ground loop. If current doesn't have a path back to its source, it won't leave the source. Okay, let's go a little further here. Misconception 3. AC reverse polarity is not hazardous. Many tools have switches in only one of the two conductors serving the item. The switch is supposed to be on the hot conductor or the ungrounded conductor supplying the power. Electricity takes the path of least resistance. I think this is my favorite myth. That has never been true. Electricity takes every path available back to the source. It will take any conductive path, high or low resistance, according to the law of proportion, in order to return to the source that provides it power. The human body is one of those conductive paths of resistance that it will take back to the source. For those of you who are familiar with resistors in a circuit, have you ever seen current skip a resistor? If it's good, if it's burned out, I understand, but if it's a good resistor, does current skip that and go on to the next one at any time? No, it takes that path back, and the human body is a resistor. It can be a path back. The danger, as we have seen, is that small amounts of current will flow through paths of high resistance. It only took 120 milliamps on a 120-volt circuit to go through 1,000 ohm resistance of a person, but it was 20 times the current to do some damage, even at milliamps. Okay? Food for thought. Okay, myth number 2, double insulated power tools are doubly safe and will always provide safety. Double insulated power tools can be hazardous if they're dropped into water, energize the water. Electrical current can flow out of the power tool and into the water. Myth number 3, it takes high voltage to kill. How many of us have believed or heard that? 120 volt AC is not dangerous. Anybody out there ever heard of that? Okay. Current is the culprit that kills. I believe, in my opinion, 120 volts is the most dangerous form of electricity or voltage on the face of the earth. Why? Because people respect high numbers. They respect 240, 277, 480, 600, but they don't think they can get hurt by 120. And as we've seen, it will kill you just as dead. Voltage is a factor in determining how much current will flow. Of course, time and path also play into it. A sudden and accidental stimulation of the body's nervous system by an electrical current. Now you think about that for just a moment. Even if you have just a tickle or just a bite, that pressure that pushed that current flow through to make you feel that, push that through the nervous system. Okay? What do you suppose that did to the nerves and so forth? Current will flow through the body when it becomes part of an electrical causes are many. Okay? Here are some of the effects that current can have. We have shock at 3+ milliamps, muscular contractions at 10, 30 milliamps can give respiratory paralysis, 50 milliamps, the heart can be fatal, and so forth. Other injuries or burns, falls off ladders and things or off of high places when being bit or surprised, injuries when machinery starts suddenly. So we have a blackout, tagout. So we have all the procedures in 70E. You know, thermal burns, light, hearing blasts, flying debris, all kinds of things. And 70E will help us understand how to deal with all of that. Current passing through tissues generates extreme heat. Skin damage at entry and exit. Internal tissue damage results from arcs or flashes, blinding light, thermal burns, and so forth. From overheated wires or equipment or fires. All of these things are things that are hazards, and we are able to deal with them by learning what 70E says, because these people have done the study for us. NFPA has done all of this work for us, and now it's at our fingertips. We just need to be taught how to use it and how to use it properly. All right, NFPA 70E 130.7C16 and an informational note on informational note 2 on page 39. If you get a chance, look at that, because we haven't talked about trauma injuries and other injuries. That is not addressed by 70E just yet. They're working on it, but we don't have calculations for that just yet. Falls could be initiated by shock. Muscles contract involuntarily. Workers can lose their balance and fall. Again, unexpected activation of machinery, injuries, shock, pinch, crush, could be sheared. These are some things that could happen. And again, hazards are always present. Now think about this. If it's a final thought here, hazards are always present. Even if they're not identified, and even if they are identified and we're not there, the hazard is still there, isn't it? Voltage is always present at an energized circuit. It's always there. Whether we leave and go to lunch and come back or not, it's there. The closer proximity to the hazard, the greater the risk. And we looked at some of the electrical hazards, some of the electrical risks that electricity presents. Bare conductors, insulation failure. How many of you have seen insulation on the conductors, wires and so forth that is falling off or that's damaged or cracked or dried out? Equipment failure, broken breakers, broken disconnects, and that sort of thing. Static electricity, heating or overheating because we didn't calculate the load correctly or install it correctly. Electrical explosions, the lack of maintenance on systems and equipment. Again, how many of us maintain our electrical systems? Things to think about. Overhead live overhead wires are the most common. Working on rooftops, repair of electrical systems, capacitors or another. Why would there be an issue with capacitors? Because they store electricity, right? They store a charge. Insulation failure on cords, heat that's developed by temperatures, moisture, humidity, mechanical damage, rodents. One of the top 10 causes of arc flash in main switchgear are rodents getting in through the pipes that are not sealed and getting across live conductors. When you're pulling wire into a piece of equipment, please clean up the wire pulling lubricant, because if it makes contact between a live terminal and the casing, when it's energized, it's conductive and it will blow up. Okay? Just a word to the wise there. Chemical incompatibility, two dissimilar metals, these are all different things that wind up creating a problem for us. Other portable tools, energized housings. Remember, if there's no path back, the equipment remains energized and you come up and touch it, you are now the path back. And milliamps is all it takes, right? Broken connections, arcing faults, wrongly placed internal wiring, lack of a grounding plug. So how do we identify and deal with all of this? Again, NFPA 70, the National Electrical Code, talks about proper installations of our wiring methods, of our disconnects and our equipment. NFPA 70E tells us proper identification of and calculation of the risks and hazards involved. Then it helps us to know what procedures to put in place, what actions to take, what actions not to take, and as a final, the personal protective equipment. The biggest thing that we encourage is to shut it off. Turn it off unless it poses a greater hazard to shut it off. I'm not talking about an inconvenience. I'm talking about a greater hazard, correct? All right. OSHA will tell you what to wear what is appropriate. In other words, they tell you if you're working around electrical equipment, wear what's appropriate, but they don't tell you what that is. 70E and instructors will. All right, static electricity can create some problems, flammable liquids and so forth, overheating and so forth, abusing electricity, overloading, hot surfaces, and all those sorts of things. Okay. Last thing here is the rapid overheating from currents caused by short circuits, power surges, or lightning, heated oil-filled breakers or transformers, and then capacitors subjected to the wrong polarity. All of this could result in rapid disassembly of circuit conductors and equipment parts. Now I'm getting up to the time here, so I'm going to try and back out of this if I can. Thank you very much for your time and attention. Please give attention to the website. We thank EasyPower for allowing this demonstration or this presentation. If you have questions, I'm sorry that I've run out of time, please email them to me or please call me. And if you need some assistance with setting up safety programs or with doing any of these other types of things on instruction for, and I'm going to say thank you and I guess sign off.